Yeah. Okay. So we want to start with the session 1, computer science, computer engineering. This session will be 5 talks. 4 of them will be online, one live. So perhaps we could move the last one to the second one, the one that was moved over. We will see. We will start now with the session. Okay. The session is support vector regression under percentage error losses. Okay. Wait, we cannot hear you. Check the mic, please.
Okay, can you hear me now?
Okay. Yeah. Okay.
Yeah.
Thank you. Good morning. I'm Pablo Benavides Herrera from ITESO, and I'll present our work on adapting support vector regression to minimize the percentage error loss directly. So a little bit of the motivation behind our paper. In forecasting and control, stakeholders judge errors relative to their target scale. So for example, a $10 miss on a $10,000 project is fine. However, a $20 on a $20 project, it would be catastrophic. That's exactly what MAPE captures. MAPE is widely reported in business dashboards, energy load studies, and forecasting competitions. But most models, including classical SVR, don't optimize it directly. They minimize an absolute loss, which creates a gap between training and evaluation. We want to close that gap, keep the convex, kernel-friendly SVR machinery, but optimize percentage error so training reflects how we actually judge. So before introducing our reformulation, let's quickly recall the standard epsilon support vector regression, or epsilon SVR. SVR finds a flat function in a possibly infinite dimensional feature space. Points lying within this epsilon 2 are treated as accurate enough. Only those outside contribute to the loss. The regularization parameter C controls how much we punish deviations outside the tube. So it's the trade-off between bias and variance. All the magic of nonlinearity comes from the kernel trick, where we replace inner products by a kernel. This structure, convex, kernel-based, and efficient, is what we want to keep intact when we move to percentage error loss. So as we said before, classical SVR optimizes absolute error, but MAPE, or the mean absolute percentage error, measures relative errors and is scale invariant, the metric actually used in real forecasting competitions and industrial reports. The issue is that the MAPE division by YK breaks the symmetry of SVR constraints, so it isn't optimized directly in standard kernels. Our goal is to embed this loss directly inside SVR while retaining its convex and computationally efficient formulation. So, moving to our main results, here's the full primal form of our SVR MAPE formulation. As you can see, we start from the standard epsilon SVR objective, but we scale every constraint by y once divided by yk, so that residuals are expressed as percentage errors. You can see that the modification is done in the constraints, the restrictions. That division changes the geometry. Samples with smaller targets now have wider feasible tubes, When we carry this through the Lagrangian, the dual problem remains convex, but its box constraints are scaled now as C over YK. The kernel trick still applies, so this formulation can be solved by any standard SVR implementation after rescaling C and epsilon. Computationally, nothing changes. We just measure error the way practitioners actually do. Next, I'll show you the dual formulation and why convexity and kernel structure are fully preserved. So here we can see the dual form derived from our primal optimization problem. You can see it's structurally identical to the classical epsilon SVR dual, a quadratic term in the Lagrange multipliers and one equality constraint. The only difference is that each observation now has its own box constraint proportional to 1 over YK. Because the kernel term appears unchanged, convexity and the kernel trick are both preserved, meaning any standard SVR solver can be used after rescaling C and epsilon. So we maintain the same computational cost, but align the loss with percentage error. So moving now to our experimental setup, we evaluated our formulation on 3 datasets, two public benchmarks for reproducibility and one industrial energy load dataset from external validity. All baselines were tuned fairly using Bayesian optimization with MAPE as a target metric. Each configuration was run over 30 random splits to ensure statistical consistency. We measured the R-squared, RMSA, and especially MAPE, since our goal is to directly minimize the percentage error. The code and experiments are open source for full transparency. You can check our GitHub repository for the code as well. So to compare our models, we used linear regression, random forest regressor, XGBoost regressor, classical SVR, our proposed SVR MAPE model, and we also used our model with a symbolic feature transformation as well. So our results are as follows. On the Boston housing dataset, the SVR MAPE delivers clear improvements, as you can see on this table. We see a reduction of 12 to 18% in test set MAPE compared to strong baselines like XGBoost and random forest, while R-squared and MSE remained comparable or even better. The scatter plot shows that most predictions lie close to the diagonal, and figure shows indicating that when the map is minimized, the MAPE is minimized, the model may sacrifice a tiny bit of R-squared, which is expected. Most importantly, all this comes without changing the solver. We just rescale C and epsilon in a standard SVR implementation. So as you can see on this table, once again, it not only overperforms from XGBoost, but from all the other metrics, or even using the classical SVR. So this makes sense for us to minimize directly the SVR MAPE. So to wrap up the analysis, here's what the formulation means in practice. Theoretically, we proved that introducing 1 over YK scaling preserves convexity and kernel compatibility, so we don't lose any of the guarantees that make SVR appealing. Practically, this makes SVR MAPE a true drop-in replacement for existing solvers. You just need to rescale parameters and train as usual, yet you directly minimize the metric most practitioners report. So we are not proposing a replacement, an entire replacement for the classical SVR, only when the MAPE is the metric that we are trying to minimize directly. And computationally, nothing changes but the same solvers, the same complexity, but with consistent percentage-based accuracy gains. In conclusion, we've shown that you can reformulate SVR to minimize percentage error directly while preserving all the mathematical and computational advantages of the original. This small but fundamental change aligns model optimization with how forecasting accuracy is actually judged. Looking ahead, we plan to extend the formulation to handle zero or negative targets and to incorporate it into online learning frameworks. We believe SVR provides a practical foundation for percentage-based regression in both research and industry. Thank you.
Okay, thank you.
Now I'll be available if you have any questions.
Okay, yes. Do you I'm wondering about the results of the optimization, the variables. They keep the same values or also a scale? The set magnitude there, I cannot see them from here, but yeah, that's my question. Yes.
Yes. Can you repeat the question once again? Sorry.
Yes, because now the problem when you are optimizing the percentage will be a scale. The results are also a scale, or keep it like the problem without using the percentage of the loss function.
Okay, so we rescale the results for the model, but when we show the results once again, they are in the actual scale of the data, because this is most important when forecasting. Whenever you do any scaling or any transformations, you do it just for the model fitting. But once you present the results back or the actual forecasts, you have to do the inverse transformation or anything you did just to show the values in the actual scale.
Scale. Okay. Good. Okay. Thank you. Thank you for your presentation.
Thank you.
Okay, I have in my schedule, the next one is the ID 30. Okay. You have a different schedule. So, would it be possible the presenter of the ID 100?
Daniel Estrada.
Yes, I hear.
Okay.
I am the next.
Okay.
Daniel Estrada.
Okay.
Okay, I am the next.
Yeah. Yes, please.
Okay.
Go
Okay.
ahead.
Can see the presentation?
Yes.
Can see me?
Yes.
Okay, okay. Hello, everybody. My name is Daniel Estrada. I will present the short paper entitled Structural Complexity Metrics for WorkForNet. This work has been developed with my thesis advisor, Ernesto Lopez Mellado. In this paper, we deal with the structural complexity of RTNet models. We overview several complexity/simplicity metrics for comparing model discovered from the same event log. For these pertinets, we want to determine which the hash net more complex has. The presentation structure follows. First, I will present the context of the problem. Then I will overview for graph complexity metrics found in literature. Afterwards, I will present the application of submetrics to set of model. Finally, I will sum conclusion and outline current research. This work is the context of process mining, which comprises of three main stages: discovery, evaluation, and enhancement. The application of the process mining is on discrete event process. For example, the industrial process or business process. In the discovery stage, the behavioral process in the form of event sequence called event log are tried to obtain the suitable model to represent such a behavior. The evaluation stage applies for quality metrics to assess the characteristics of the model regarding the log. In general, the evaluation requires information for both the model and event log. Finally, the enhancement stage utilizes the evaluation result to provide adjustments of the process or the model to improve the process operation. Model evaluation. There are four quality metrics to evaluate the models. The first is the fitness, verify see if event log lambda is present in the model. Precision, estimate the plural language of the model regarding lambda. Generalization, model behavior, this is not in lambda. Simplicity concerns the structure of the model. Our paper deals with evaluation step, focus on the measure model characteristic, the simplicity or complexity. The aim of this paper is provide a measure that qualifies the graph structure regardless the event log, to compare two or more models to replace the same event log. For example, this Petri net, excuse me, this Petri net represent the same event log, but the upper wheel is to maximize the precision. However, it's structural more complexity. In this paper, for study the metrics on literature and adapt the evaluate to be part the graph or warfare net. Apply the metrics to prior model for comparing purpose. On this overview, we found four metrics to evaluate the structural model. The first one is the volume. It's a metric proposed for Garrison and which had been proposed for software analysis. This logic is the large model have a structure that is more complex. For example, the following net represent the same envelope, but each one be obtained by these different methods. The volume is evaluated is one, as can see the is higher second net. However, you can perceive the first is more complex. For example, the net of the left have a similar structure to a cycle, and the right is only sequential executions. The second one is the density. The density which is proposed by Mendeley. This method reveals how related the vertices is defined a ratio number of arcs over number of vertices. When we apply the metrics of the previous net, can notice the first net is more complex than the second one. This evaluation is different than the previous one. The next is the cyclomatic number, was proposed by McCabe for software analysis. It's called a cyclomatic number, which compares the number of arcs or number of vertices. This follows the same logic of the previous one. The larger cyclomatic number, the more complex the model is. We apply this metric to the previous model, we obtain values which we can draw the similar conclusion. The net in the left is more complex than the right. The next is the coefficient of complexity or CNC. Is different. It is defined the ratio between the number of possible execution enabled by the model and the number of nodes. It's important to say the language of the model must be finite. The evaluation follows the logic that the smaller value of the CNC, the more complex the network is. When we apply this metric of the nets, I give a result similar to Boolean, which states second net is more complex. This metric, this value is smaller, is more complex. Now, we are going to present the application of these four metrics, a few powerful models. Discover how the different methods for the same event log. In this example, the upper net is more precise, is more complex than the lower net, and the metric confirm this fact except for the CNC. In the table, you can see these values. Volume, we have a notable difference of 22 units, and the density unit a difference of 0.63 units. In the cyclometer number, I have a difference of 17 units. However, the CNC don't show a large difference. In this example, the opponent appears more complex and the metric values confirm this observation. The volume show a difference of 7 units. The density have a difference of 0.23 units. Regarding cyclomatic number, we have a difference of 4 units. And CNC is a minimal difference. In this example, the model is similar. The upper net has 2 more places, here and here. The upper net has a precision equal to 1. Is replaced only the trace the event log. Instead, the lower net for traces that precision 0.5. The application of the metric reveals that the first net is more complex. Volume have a difference of 0 units, 6 units, sorry. The density have a small difference of 0.08 units. The cyclomatic number difference of 2 units. And the tau nader model has a structure similar to cycle. Can you see that this net is not have a cycle, only has a structural or sequential location, but the cyclomatic number is more large than their net is in the down. Conclusion. The study overview for the structural complexity measure for pretty nets. The metrics are applied to para model for comparison purpose. All measure can differentiate the relative complexity between the nets. Density is the most effective measure because it estimates the degree connected among the vertices of the net. They may be a correlation between the complexity or simplicity and precision of the model. We believe that model only more spool language are simple. And for example, the previous net, the next is more small, is a precision lower, and this represent the relation. When aggregate the two places, maximize the precision. Ongoing research. Now I will give online a current research for a metric simplicity / complexity. In the proposal, we held the density metrics, and then we combine a measure of graph regularity. The density relation with this equation. Here you can see these two graph. This is a tree. This is a complete graph K6. Then introduce the concept now if we evaluate the density of the trees, we obtain density equal to 1 in these trees. Then we introduce the concept of regularity in this equation, which measure the order in the graph by analyze the degrees on the vertices. Then the regularity compute 1 minus to equate on the standard deviation on the vertices degree over the average of the such degrees. Thus, regularity or regular graph is equal to 1 because the standard deviation is 0. Then applicate this measure to the previous tree. We can distinguish degree of complexity of the graph. The lowest value corresponds to a more complex graph. We can combine the density metrics with the regularity measure. The complexity is computed as density divided by the regularity. In this example, the regular graph is equal the complexity given by the density. Then the complexity previously is computed. So now I can see the density is 1. Otherwise, the regularity is a lower value. Then we apply the metric to the previous pricing pertinence. We obtain the values that distinguish clearly structural complexity of the net. The algorithm measures the complexity computed by the density metric. We believe the introduced metric is suitable for the structural complexity of a model. However, we need a further research. That's it, and thank you.
Okay, thank you. Questions, comments? How do you define the density? Because I think it's only related with the size of the net, no?
No, it's density relationate the value or grade or relation the nodes. If the node have I need the presentation. Excuse me, give me a second.
Yes, we have time.
In this tree, the density is 1 because the all nodes have one relation.
Uh-huh.
When the density is more large, because the nodes have a more relation between the nodes. When the nodes is more large and his nodes more have a more relation, the red is more difficult to see the relation between the node 1 and the node 2, because these nodes have a more relation, and this is more difficult to see or follow the relation between the nodes.
Okay. Questions? Okay, thank you for the presentation.
Thank you.
Thank you. Now we are going for the fifth, and we are on schedule now. The paper with ID 98.
Really?
Okay.
Okay, good afternoon. I will introduce this paper. Okay, I am the first author, Matias Alvarado. My co-authors are Javier Rivas and Yolanda Vázquez of the Technological University of Panama, Faculty of Science and Technology, and me from the Department of Computer Science here in Sinsla. Okay, the agenda of the presentation is this. I describe the challenge, the antecedents, the related works, material and methods, results, and future. Feel free to interrupt, to ask any question you wish. Our challenge is apply machine learning in triple negative breast cancer patients to identify responders to immunotherapy. And it means find a biomarker, that means genes, to identify patients most likely respond to immunotherapy. Because in the antecedents of this work, we observed that, that this immunotherapy were applied, but a lot of patients may not respond to this therapy. So our challenge, Javier Rivas' challenge, was identifying when some patients are more likely to respond to immunotherapy. And question was, how will you do this thing? And Javier thought by identifying the genetic profile of the persons. And it means use the biopsies samples and analyze with some bioinformatics tools, and then apply random forest for this task, as I explained. And it means find one biomarker. One biomarker is a functional structural elements that combine to characterize a biological process. For biologists, for medicines, this is very useful. And this is the task now with artificial intelligence, machine learning tools. Apply home. Then we wish to find the genetic profiles of responders or non-responders to immunotherapy against triple-negative breast cancer. But next I will explain. It means identify main genes in the patient biopsies in immune cells T, B, and M. T cells, they are named this way. They are the cells that attack the sick cells in the tissues to avoid any sick. Of course, they are specialized for each disease. Okay, and B, well, and now I will explain. Our challenge context. Biologists and physicists, they has materials, cells, biopsies in glasses, and they perhaps have hair, cells, enzymes, and emulsions, and so this handle this kind of information in clinical context, in clinical facilities. And this is the tumor tissue sample, and they extract data. And for genetic purposes, they do sequencing, okay? And we used this information to try to do data analysis and the visualization. Okay, apply the machine learning tools. This is our context. And data that we used is from projects of Xiao in 2024 and Bases 2021. And it reduced to 45 patients, biopsy samples with triple-negative breast cancer that were treated with immunotherapy in one specific immunotherapy. That is the immune checkpoint inhibitors. And now I will explain what means. Okay? And this is ribonucleic acid from tumor biopsies that was sequenced at single cell resolution. And this is called this in the context of. Okay? Antecedents. There is a high human and economic cost about breast cancer. Some data, main challenge for public health worldwide, and is the cause of highest incidence and mortality in humans. For instance, Panama, because my co-authors, they are from Panama, is 40% of all cases in all cancers during the last year. And in Mexico, in one note that appears in La Jornada 2 days ago, says that in 2023 had 8,034 deaths. Sorry for this. And it means this amount, Mexican pesos, in medical services, and the work cost for absence and so, 9,000 millions of pesos. And usually, cancer is increases because of feeding, contamination, aging, and so on. And this data is from human above 20 years old. Okay? Now, the immunotherapy in triple-negative breast cancer. Triple-negative is because there is, in this cancer, no receptor to estrogen, progesterone, and epidermal growth factors. Okay? This is the name. And this is around the 15% of all cases has poor capacity of prediction. It's complex to predict this kind of cancer with the traditional methods. The method to treat this cancer is chemotherapy, as most of the cancer so far. And immunotherapy means, as an alternative, strengthen the immune system response to cancer fight. Okay, I explained how. Okay, the how is the immune checkpoint inhibitors, EC, that means continual immune response mechanism. Okay, and I explain here. The immune system responds against one lyse, but should regulate. At some moment, should stop. Because if not, can be leukemia and lyses like that. So, immunotherapy in some cases means continues the effect, continues. And it means in this case, PD-1 and PD-L1, they do the killing of tumor cells. And usually immune system say stop. But for immunotherapy with IC, it means no, not stop. So send anti-PD-1, anti-PD-L1 that allows the effect, okay, and that continues the immune response. Okay. And this is now, and in the other side, the machine learning perspective is to analyze, big data sets and late use for predictions. For doing, in our case, cancer prognosis prediction. Okay, and to identify key genetic patterns in immune response with these samples of cancer, breast cancer. Okay. And data, as said before, is from this project, this amount of biopsies, samples, and in these conditions. Okay. Since the computer science perspective is data collection, data preprocessing, extraction of main feature by using a random forest to extract key list. Okay? The cells, the group of cells that we will focus is T cells, as mentioned before, that they are the cells that attack cancer cells, the B cells that they produce antibody, and the myeloid cells that they are responsible for innate immunity. Okay? They should give extraction of active gene list, and of course we need to normalization of data to are good input to algorithms and generate the gene expression matrix. The gene expression matrix is the way that genes, they are interacting for producing some configuration. It means the genes are the same, around 24,000 of genes. And the way they interact is the tissue that determines if shape, eyes, or hair, or lung, or disease. So it means, and the gene expression matrix is regarding this triple negative breast cancer. Okay, and the immune response. Okay, this is in our case, the gene expression matrix. Okay, this is the mathematics applied to do normalizations. Okay, learning purpose in high school or on the first semester of degree. Use the logarithmic transformations. Okay, and when the data are normalized, we apply the machine learning algorithm from machine. The random forest means a set of trees. Decision trees, we know that they are very useful to decide, to classify in one population regarding certain characteristics. Okay? But the problem when we use one tree is that the origin, the way to construct the tree, can bias the result. To avoid that, one person think two different trees with different way to be constructed, and after that, do analyze, do statistical analysis with the results of this set of sample, but good, very good. So we have multiple decision trees training for combined predictions. Okay, and bagging in this process, the bagging is when it started with the replacement of the original data to create multiple training sources. Okay, and then after training different trees, this is the process of overlay. The most trees said about the thing to be classified is the way to characterize. Okay? And it is a democratic method, and has high performance in binary classification and beyond, not just in binary classification. Okay? This is the details of the algorithmic setting. Perhaps Javier, the co-author, wish explain online this chat. Yes, Javier, or?
Yes, I'm here.
Okay, come on, please.
Good afternoon. We, for each cell group described later, for each cell group, we carry out the process described in the image on the right. We first step was to do a random splitting data using stratified cross-validation because we want to keep a proportional number of responders, patients, and non-responder patients from in the set of training, in the set of validation and test. The only parameter that we changed was the number of the decision trees, because we want to see the robustness of the model for different configurations. For example, if we have 5,000 genes in test cells, we perform a simulation with 5,000 trees, decision trees. In the next step, we do the same, but with a half of trees. In this case, 2,500 decision trees. And then, until a fifth part of the number of genes. In each simulation that have a good performance, like 0.929, more or less, 13/14 good predictions, we capture the characteristics that give us a better prediction with the attribute future importance. To know what was the characteristics that gave us the better predictions. This is in the final step, we do an intersection of these 5 lists of better characteristics to do an final list of K genes for the better predictions.
Okay, Javier, thank you very much. And the results, they are here in each simulation. The accuracy is above this number, so it's very good to choose any key genes. And regarding the sets of training and test, we separate 31 for training, 14 for testing. Known responders were 21 and 10 respectively, and responders 10 and 4. In this case, is the third part, more or less. In this case, is around the third part as well. See the active genes for cell groups and key genes got by random forest is in this amount with T cells. There are these 4,000, almost 5,000 genes, and the key genes are identified 240, that it means 5%. And in B cells is the amount of active genes. And in this case, the key genes are around 14%. In myeloid cells, it's almost 1,000, sorry, and the amount is 7%. And in the combination of all of these cells, this is the amount, almost 5,000, and the key genes, they are in the order of 4%, more or less. No, 5. Oh. Yes, 5. And so, context of our results, one traditional tool for analyze the genes is the functional enrichment analysis. This is very well known in biological fields for identifying most enriched function. And it means the biological process regarding T cells, okay, the very important cells in this immunotherapy. This is the tool used for, and the results, it means that response patient with these key genes identified with a random forest has these key capacities. Particularly, I explained this tool for a computer science public, that is the effective cytotoxic and pro-inflammatory responses. Cytotoxic is the capacity to kill the bad cells. This is the cytotoxic. And pro-inflammatory, it means that when one tissue is bad, it's inflamed. And this is the capacity to deal with this for this response. Okay, and the resistance to oxidative stress. Stress is one thing that damage the cells, and in this case, the key genes identified has this property. So identified genes will be key for predicting clinical responses to immunotherapy in triple negative breast cancer. So conclusions, random forest to genetic classify responders to separate of non-responders to IC therapy as a biomarker is a useful tool to identify these biomarkers. So the gene signature in T cells for identify this relevant biological process that may explain the immune response in this case of immune therapy. So future work, of course, the sample size is small, but there is no more, may provoke overfitting. So if we add more data as soon as possible to that, will be better. Use explainable artificial intelligence is a good option. Actually, Javier did some exercises about that, and perhaps apply this kind of techniques for quantifying each variable contribution. Is some of the references, and thank you very much for questions.
Questions, comments?
Yes, please.
How do you find the type of data that you introduce into your machine learning model?
How
So how do you find the type of data that you introduce into your machine learning model?
Okay, yes, this is because in one of the papers that I mentioned, the paper in 2021, we find that this author used these biopsies to identify using machine learning other kind of networks since the biological point of view. And the data set, they were very well worked, very well formatted. So it was very, very nice to use this data. So it means that this one paper concerning immunotherapy against breast cancer, triple negative breast cancer. Actually, this is the reason that we focus in this cancer, because we have this very good data. But this is the point, because sometimes you can think, I apply this tool for, but if there is no data, you can invent, of course. But if there are some available data, proof data in one good publication, is for trust data to use for report. This is the answer. Thank you, very well, very good question.
I have a question.
Yeah, please.
How can you get more data from Mexico? Because I guess that in Mexico we have a problem with the data, with the hospitals or something like that. Can you explain how in Mexico it would be possible to use this kind of
This is the main question and illusion I have. Yes, because perhaps with some partnerships with some hospitals, it could be possible. In our team, we have one immunologist person graduated here in Silverstad, in the biological department of America, and he works now this month from his postdoc in New York. So by his via, we can find the adequate data in Mexico. Yes, because this is a problem.
Yeah.
Standardization to give this data.
Yeah.
There are some protocols, very not very measured protocols, and we need to work on. Yes. Thank you very much. Yes, please.
As the presentation said, we use like a lot of data. The consequence is another critic. So, well, I know that in these cases, we need to use a lot of data, but how do you avoid like the overfitting?
Well, perhaps with this data, we cannot properly avoid. we prevent about these circumstances. Adding more data is the option, and perhaps using additional data, actually we find other data sets in one paper published this year. And actually, this is not work. We test, Javier test the performance of our method, our algorithm with this new data set. And the result was good. In this range of goods, of course, we can generate artificial data. This is the other possibility in this hard circumstances in platform. Really better. Thank you. Thank you. Yes. Okay, this time is over.
Yes.
Okay, thank you.
Thank you very much. The next presentation is automatic classification for American Sign Language using bytecode.
Yeah, it's me. It's visible, right?
Yes.
Okay, well, I'm going to start. Hello, everyone. My name is Francisco Javier Moreno Vasquez, and I'm going to be presenting you this short paper called Automatic Classification for American Sign Language using PyCaret. This is a brief outline of what I'm going to be talking today. First of all, what is the American Sign Language classification? First, the American Sign Language is a manual alphabet for the communication between deaf people widely used in USA and some parts of Canada. The first motivation to do this classification is make communication accessible via automated recognition in some devices like cameras, video calls, and the common approaches to do the classification are the convolutional neural networks. However, these neural networks are computationally heavy. So addressing the issue of the heavy, why study machine learning and auto ML? Well, the main purpose of this thing is to have lighter models that can be deployed on devices like microcontrollers, ESP32, even in cloud environments. So after this, if we are going to choose some machine learning model that there are several of them, then the automation of the search of the model is crucial for us. So in this case, some libraries, as in our case, we are using PyCaret that simplifies the model selection and the hyperparameter tuning. And as well, with all this, we can address another topic that is the dimensionality reduction that can be useful to reduce the input size and the speed of the training and the performance of the accuracy in the models. Now what we use is this dataset, as we can see, has all the sign languages. Well, not all, because if you can see, it's missing the J and the C. This is because these are layers that need to be performed with movements. So we remove it from the dataset and we only have like the static layers that can be used as photograms in the training. Also, the pipeline is quite simple, but you can see that we had two data sets. The first one is the original one. After that, we applied some data augmentation techniques that, as is very known in this topic, the data augmentation is well for the convolutional neural networks. However, we wanted to explore if this is as useful with the machine learning models. And after that, we do all the pre-process and training, that is the dimensionality reduction, train with the framework, choose the better model, and finally evaluate it. Now, the dimensionality reduction. We studied three different methods. One of them is the principal component analysis. That is one of the widely used methods that allow us to find linear linear relations in the data is fast. It's a method that is very, very fast. Sometimes it's not as accurate as another ones, but allow us to give orthogonal direction of maximum variance that in some cases is very useful. The second one is the linear optimal low rank projections. This is an evolution of the PCA using the objective variable. This is a supervised linear method as well because it's an evolution of the PCA. It's useful in high dimension, like in images, and sometimes has some issues with the low sample size problem. So we need a very big data set to do it and extract all the features of this. And the last one is one of the most recent methods that is called UMAP, Uniform Manifold Approximation and Projection. This is a non-linear manifold learning. The other two was linear, this is not linear, so help us to find another kind of features and characteristics in the data and preserves local and some global structures, so it's useful, not as the other ones that can be restricted to the local features. Now, the PyCaret experiment. First of all, why to choose this library? There is another well-known library called LazyPredict. However, LazyPredict only gave us the models and the evaluation on that. But PyCaret is, as well as LazyPredict, a wrapper of scikit-learn, XGBoost, LightGBM, and CatBoost. So it has more of the recent like models to study, but provides a whole pipeline, the pre-processing, the model comparison, the hyperparameter tuning. These characteristics on this library make it perfect to do a whole research and see the performance, not only some metrics like the error to score, the errors. It allows us to go further into a research of the choosing of a model in machine learning. And as well, this facilitates the benchmarking of many classifiers quickly. This helps us as researchers to improve and make faster decisions in the model. Now, the results and discussion of this. First of all, we have here a table with all the models and the dimensionality reduction techniques that we use, and we can see that the non-linear, that is UMAP, has the better results. And this is very useful for us because sometimes we can guide us only because PCA is fast, because it's easy to apply. But in the selected topic or problem that we are addressing, maybe it's not the best dimensional reduction technique that we can use. And these kind of tools as the PyCaret help us to analyze fastest and help us to focus on another things like how to pre-process the data. That is a very important topic in this case. And also we can see in the model that some of the models that are choosing here, or the prevalence here, is the tree-based models, random forest, extra trees. And also this is another problem in the machine learning world, that sometimes because the model is easy, like I don't know, KNN, linear regressions, we can choose these models, but it's not the best for our problem, and we can improve this thing using tools like the automation in the machine learning pipeline. Now, the discussion for this paper, we can see that UMAP captures all the non-linear relationships, much better separability in 2D embeddings, because we did the components with only two to make it visually to the human eye. Also, PCA and low are linear faster, but underperform is what I told you. For this data set, this kind of dimensionality reduction are not the best suitable for us. And also the augmentation here, if you can see in the table, all the augmentation data is not the best approach for us. Even with the convolutional neural networks, we know is well studied that the augmentation is useful. For our case, using machine learning models, using traditional machine learning models is not the best case to use in this topic. So, as I hear you said, may harm classical ML by adding synthetic artifact, because at the end, the augmentation is synthetic artifact. No, as the final conclusion for this presentation, well, classical machine learning models with novelty dimensionality reduction techniques as UMAP produce the best results among the tested dimensionality reduction tests. Also, as I've been told all this presentation, PyCaret proved useful to rapidly compare many classifiers and tune models. Also, the embeddings plus the AutoML is a promising route for lightweight, in this case, American Sign Language recognition systems, because we can apply it to cloud environments, microcontrollers. And also here, I want to remark something very important, that the dimensionality reduction is not only for these kind of topics of computer vision, it's used in a bunch of other topics as digital twins. And to have all these techniques well proved and with a framework that allows us to test all of them with very much effort for our part and focus on an important topic, I think it's very useful for this research world. And following this line, the future work for this could be to test the convolutional networks versus the classical methods on-site hardware. I mean, in maybe on cloud, like AWS, GCP, Azure, or even in devices like a microcontroller, an Arduino, a PIC, etc. Also explore, learn domain-aware augmentation and statistical tests for significance, and see if this is helpful for our research. Also the ensemble models, because we are here only using the pure model, not making bagging, not making ensemble. So maybe doing an ensemble of the models can help us to do a more to improve the accuracy of the model through the hyperparameter optimization. That is a feature that PyCaret as AutoML framework allow us to do with these two libraries of Tuna and HyperOpt. And also maybe we can use a more recent data set, maybe search for another source, or even we can do our own data set. I think that's all for my part. I don't know if you have questions, something to say.
Thank you for your presentation.
Thank you.
Questions, comments? This was one of the things that I thought is you don't use this augmented data. You can create your own data. You can have all the people and taking the photos. That's the best, I think, that you can proceed. Our question is, have you tried this module from convolutional neural networks from Google that give you the skeleton of the hand? No?
If I try to use like this commercial,
no, it's free. It's free. It's not commercial. It's free.
Can you repeat which model?
It's a Google offer, but it's free now. You give the photograph or a video of your hands and give it this device produced some years ago. What's the one? Well, you give it the hand and produce the skeleton.
Oh, yeah. That give you the arrays and the vertices, right? Is what you're talking about.
I think with that could be easier. to learn some machine.
Well, I think
And-
that can be useful if taking what you told about taking the real data that only. So I think that it can be a very a well track for the future to take my own photos and use all these tools that allows me to better track in the hand.
And then you can use these signs that are non-static signs. No?
Yeah.
But you can track or have the data from the skeleton. Well, that's also for the future work. Okay, thank you for your presentation.
Thank you.
We go to the last presentation in this session. A numerical comparison of a novel post-processing technique for, I think, it's less significant byte detection based on a chaotic laser source.
Hello,
Hello.
hello, can you hear me?
Yes, we can hear you.
Okay. I'm sorry. Good afternoon, everybody. My name is Ixel Castillo Garcia. I am going to present my work, which is a numerical comparison of a novel post-processing technique for LSB extraction based on a chaotic laser source. This work was made also with Ming-Won Lee and Ignacio Enriquez Aldivar Huerta in Laboratoire de Physique des Lasers at Université Sorbonne Paris Nord, France, and Instituto Nacional de Astrofísica Óptica y Electrónica Puebla, México. So, okay, our outline. This is the outline of my presentation. First, I'll explain why random bits are important. Bits are especially in modern cryptography and secure communication. And then I describe
So
how
we are watching the conclusions of your presentation. Is okay?
no. Okay, sorry.
In the last.
I'm sorry. Can you see now the outline?
Okay, this is the line. Okay, thank you.
Okay, I'm so sorry. Okay, so the second is how to generate random bits, focusing both algorithmic and physical approaches, and chaotic signal generation, which is the core of my work. I am going to explain also the conventional 4-LSB extraction, which is the most useful technique for true random bit generators, and compare it with my novel PAM-N technique, and show the histograms to compare. I'm sorry, my camera was to compare the results and with NIST tests and the conclusions. And then why are random bits important? Well, random sequences are used in many fields, for example, in gambling, in simulations and modeling. But the most important application is cryptography. The quality of the random bits used in cryptography determines the security of the algorithm, and therefore the level of secure communication. And we can see, for example, like today, I think that the Sedena was hacking in the morning or yesterday. I don't remember very well. But this is an example to why is true random bits so important. But how to generate random bits? We need to know that random bits cannot be generated by algorithm because to consider truly random bits, the human cannot be possible to control the source. And then we need physical entropy source to ensure the quality. And there are three main processes, which is thermal noise, quantum noise, and chaotic signals. We are going to work with these chaotic signals. This is my circuit. I was working with this circuit. The laser that I am working with emits a light and then comes to this optical circulator, travels through the split, and the 90% of the light travels through the polarization controller to the standard fiber and to the VOA, which is the variable optical attenuator. And we can control with this VOA the feedback ratio that we want to generate the chaotic signals. And with the photo detector, we can collect the electrical signal, and with the oscilloscope, obviously, collect our signal. Our oscilloscope is of 8 bits. It was the signal collected in time and the histogram collected directly with the oscilloscope. But a random sequence must be unpredictable, patternless, and uniformly distributed. And we see that we obtain a Gaussian distribution, and then it means that it's not uniformly distributed, and because each bit has to have the same probability of occurrence. There are many techniques to solve this problem, and the technique is conventional for LSB extraction. This is the most commonly used technique, and consists of retaining only 4 last significant bits out of 8 available from the ADC. This is the conventional design of a true random bit generator. In the first block, we generate the chaos, and in the second block is the optical post-processing. Also, we need this photo detector, the ADC, and the 4 LSPS. Okay, and it was the histogram after the post-processing. But there are some disadvantage, which is this post-processing. It's made offline. It's an offline post-processing, and also we lost 4 out of 8 bits that we can collect. And as we don't, and we need this optical post-processing, so we have 3 disadvantages for this method. We are proposing a new method to avoid or to solve this disadvantage based on PAM signals. So firstly, PAM signals are pulse amplitude modulations and depends on the number of levels. In this slide, we show 2 kind of signals, a pseudo-random and regular signal. We're going to use pseudo-random signals because we don't want to introduce patterns in our technique. So this is our technique that we are proposed. Also the chaos generation, and then we put the photo detector, and then the ADC with 8 bits, and we combine with these PAM signals. So we obtain this one, and in our proposed method, all 8 bits are preserved, which means no data is lost during the process. This allows a double rate bit generation, and it's a not complex post-processing, and also the possibility of online technique. It is because PAM signals can be set up optically, but the main goal is to achieve true random bit generator without losing any bit. Okay, this is the general idea. So we collect the histogram of Curie signal, and then we combine with the PAM8 signals, and we got this distribution. Okay, I'm going to show a comparison between our method with 4LSB technique, and we can see that our methods use the entire dynamic range. So, but when for LSB technique, the range comes from -7 to 8. So the range, the dynamic range is shorter. How can we validate that our signals are really or truly random? Because, well, we use this Niels test, which is has 15 statistical tests. Each test provides a p-value, this p-value, which indicates if our sequence is enough random. We have to get a p-value bigger than 0.01 to consider random. Sorry. It was our result, our table. When we put the cows without any technique, we got this result. Only 2 tests were approved, and then when cows plus PAN8 were processed, all of the tests were approved, and with 4LSB, only 1 test failed. So, in summary, we have presented a novel PAM technique for true random bit generation, and our method keeps all 8 bits, requires no optical post-processing, and successfully pass all the Niels statistical tests. There is a possibility of online generation because PAM can be added optically. That's all. Thank you for your attention and questions, and also my email.
Thank you for your presentation. Questions, comments? How many sequences do you use in the NIS test?
NIS test requires at least 1,000 sequences. And also each sequence has 1 million bits.
1,100 sequences of 1 million bits, okay?
No, 1,000 sequences and 1
Okay.
million bits each sequence.
Okay. Good. Do you have now the full process like a system, or you measure all offline? My question is, if you have now the value of the throughput, or you random number generator?
No, I am still working offline.
Okay.
Can I come back to the slide?
Yes, please.
Okay. Okay. So I am still working offline because these results were collected the signal here after the ADC, and then
Okay.
in post-processing we add pan in, like trying to do a simulation, but we want to keep working on this idea. The second goal obviously is to obtain these results online.
Okay. And you forgot also to truly number generators are used in machine learning. All the simulations need random numbers.
Yes, yes, there are many others. There are many tasks for random numbers.
Yes. Okay, well, this is the last session of this, the last talk of this session. Okay, thanks to all.
Okay, so I'm going to stop sharing. That's all.
Okay. Yes, thank you.